hello everybody. At Crystal Quantum Computer, we realize Crystal Quantum Computing, we realize a quantum computer based on the trapped ion technology. Okay, I'm going back on the fundamentals of quantum computers that probably all of you know. So it's based on the quantum superposition. That's the first principle it is based on. So you can build some linear combination between two states on the same particle. You can create states like that. And once you have a state like that, you can bring aside another particle, and you can, by achieving a quantum gate, an operation between these two, you can untangle these two particles, which means that they are not determined one without the other. And the important point for quantum computing is that each time you bring a new particle to the untangled system, you bring also its degrees of freedom, and that is why quantum computing is able to to manipulate very big volume of information. And so that's why quantum computers are good at, is to perform computation that manipulates large volume of information. So when you want to build a quantum computer, you need first to find a kind of particle to untangle. So atom, ion, photon, electrons, then a quantum gate to perform, a physical process to perform the entanglement, then a choice of trapping and isolation. And this creates a design. And the design implies limitation on these three factors: the fidelity of quantum operation, how well you perform effectively the quantum operation, the coherence time of the particle, which means how long can the superposition of the two states be coherent, and the last parameter is the number of physical qubits. And this, all three parameters convolute together, create some logical qubits, and then aside of this hardware, that is a logical qubit, a sum of logical qubits, you need a quantum algorithm that will map every mathematical problem into a set of operations on logical qubit. The more logical qubit you have, the more powerful the quantum computer, and the scale factor is that everyone wants to increase. Everyone wants to increase is the capacity of increasing the number of logical qubits. So that is the different modules of our ion trap quantum computer. So we trap ions, so you can see ions in little 4. So you see them individually onto, that is a linear chain. So they are trapped inside what we call a pole trap, where some radio frequency fields of electric fields rotates very fast. The whole system is placed inside an isolation system where a very high vacuum is performed. And aside of it, you have a laser system with plenty of laser from UV to infrared light. And all the systems, all these lasers, they go through optical fibers, and they're going to hit the ions even collectively or individually. So thanks to these laser pulses onto the ion, we can manipulate the atom wave function. So we have chosen some strontium atom. So we take this atom, we have removed before one electron. And now we have got like an ion, a strontium ion. And by sending some laser pulses, we are capable of changing the energy value, the energy level of the last electron. And we can bring it on different levels. So you can see we can do one transition at 674 nanometer, and then a two-step transition toward an excited state called the Rydberg state. So when it's very excited, the average distance between the nucleus and the atomic core, let's say, and the electron that has been sent excited is quite big. And the point of our quantum gates is when one of these ions is sent into a Rydberg state, and when you will ask with laser to the neighboring ion to do the same, you will not be able to do it because of a phenomenon called the Rydberg blockade. And this is the basics of the quantum gate we can use. So the Rydberg dipole-dipole interaction that we use between Rydberg states, just a few numbers. So this inter-ion distance is 5 micrometers. You will remark that it's far less than the equivalent with neutral atoms. For the strontium-88 ions, we use this kind of, this exact wavelength. For a Rydberg state that is n equals 65 as a principal number, we can reach a strong interaction of 10,000 dBi. And the quantum gate duration has been demonstrated at 700 nanoseconds. That is quite fast with respect of the coherence time of an ion. And now we have looked at the numbers. We can go to scalability assets of Rydberg ions. Rydberg ions are big, they're well localized, and we can manipulate them individually by laser. Quantum gate is fast. And an important thing is that the Rydberg interaction, it doesn't rely on the motion of the ion. So that's the main asset with respect to other trapped ion technology. The entanglement, it can be performed through the Rydberg blockade that I have already explained, or another kind of quantum gate named Rydberg phase interaction. Is basically when you bring two Rydberg ions together, there is an interaction, and you can achieve a phase through this interaction. So it's called a phase gate. Yeah. And another capability of Rydberg ions that is very important is that you can have 4 bodies. You can have 4 bodies interaction. So you use the phonons of the ions while they are interacting all together, and this. So in fact, what's happening is that when you, sorry, can take back one more step. So you have the line of the linear chain of ions that are like that under certain confinement because of radio frequency. And when you release it a bit, this is going to take the shape of a zigzag. And it's at the point of the phase transition between a zigzag and a linear chain that you obtain a very special effect that is this 4 plus ions. So all the ions of the chain, they interact, and they give a very long range, a longer range, let's say, of the interaction. And this is an asset that Rydberg ion has with that Rydberg atoms, for example, do not have. So thanks to all this scalability asset at Crystal Quantum Computing, we have a target for 2028, for the year 2028, of having 100 physical qubits with a 2-qubit fidelity of 99.8, and we would like to sell first to do a quantum as a service. So a few assets, our advantages with respect to the different qubit technology. So with respect to photonic qubit, we are a longer coherence time. Well, the photonic qubits, they are able to create a lot of entangled photons together. So every technology has its own assets. With respect to other ion-trap qubit, this is what I shortly discussed by saying we do not have, rely on the movement of the ions for our quantum gates. So Mulmer-Sorensen gates that are usually used by other trapped ion technology. They are based on the fact that you have to add and to remove some vibration phonons to perform your quantum gates, while the Rydberg gate, it doesn't rely on the ion motion. So it's important because with Mulmer-Sorensen gate, after several tens of qubits, because of this, the gates are starting to slow down, while the Rydberg gate, that is around 700 nanoseconds, doesn't slow down with the number of particles that are effectively entangled. Then compared to superconducting qubits, the electrons, they are inside the medium, so they are very, very sensitive to temperature. While with trapped ions, we are still trapped very close to the material of the trap, but we are still separated from the trap. So we have a far less dependency with temperature. And compared to neutral atom qubits, in addition to the thing that I already said concerning the possibility of having a long-range interaction, also neutral atom qubits are usually trapped with what we call optical tweezers. It's like laser beams that are very, very intense, and that they have to release it and recapture it for each quantum series of quantum operation. And with trapped ions, the trapped radio frequency field are maintained on every time, so we do not face the instabilities that this release and recapture can give. So we want to create, to propose a quantum as a service, but at Crystal Quantum, we are specialists of the development of the hardware, so we will have to rely to the different partners of the ecosystem. So my associate, Luca Guidoni, is researcher at CNRS Matériaux et Phénomènes Quantiques. So we're going to do a collaboration with this laboratory. We're going to rely on the algorithm subcontractor to write the algorithm codes. We'll rely on a quantum as a service partner for interfacing with the customers, and the customers will have to send their needs to the algorithm subcontractors. A few applications, most of you know it, the cybersecurity, so it's the capability of factorizing prime numbers that from quantum computing, so you all know that. Another family of calculation that can be performed with quantum computer is the solution at the multivariate equations. So among this family of problems, you can have, like, for example, the quantum computer are capable of giving the best results to maximize the transportation of goods in the frame of globalization. So this will prevent some pollution because it will increase its efficiency. As the quantum computers, they are very well at manipulating big volume of information. Then they are a good candidate for weather forecasting. Another application is something that there has been already some proof of concept for, is quantum computers. They are very good at detecting some asymmetrical pattern in images. Like, for example, this medical radio, they're going to be able to find this asymmetrical shape, and this will increase the capability of cancer diagnosis. And another problem that can be solved has been largely discussed this morning, is for pharmacology. So the market will be around 2 billion in 2028, following from MarketWatch. We would like to get a segment of 75 million euros in 2028. The growth of the market is 35%, and following McKinsey, the market will be around $1,000 billion in the mid-2030s. And we'd like to focus to pharmacology and quantum machine learning. Donc quantum machine learning, so this is a part of quantum machine learning. I didn't say it. And so we would like to achieve a higher computing power, thanks to our scalability asset, in order to sell it, even to specific consumer segment via the myriad of quantum algorithm developers. So the first years, as I said before, we'd like to do a quantum as a service, and later we'll do like some of competitors to sell directly some quantum computer for on the sites of the data centers where they are. So we fully integrated machines. So the company is from March 2021. We are incubated at the Telecom Paris incubator, and we have started recruiting in September 2023, and we are now doing our fundraising. The first year we will focus on the R&D on the ion trap. The second year, from the fundraising, we will develop the laser system and the vacuum chamber. After 2 years, we'll do ion trapping, and we realize the quantum gates. In 3 years, we'll validate the quantum computer. By validating, I mean using all the scalability asset of Rydberg ions to get a better computing power. And in 4 years, we'll do sell quantum as a service. So these are our sponsors and partners, Incubateur Télécom Paris, Pôle Systématique, BPI France, French Tech Paris-Saclay, France 2030, voilà, and IGEU. We thank them very much, and I thank you, and I'm available for your questions.
We have plenty of time for questions. Any questions out in the audience? Oh, here we go. Thank you.
Maybe it's technical, but you mentioned many body effects that are long range in these ion chains.
Yes.
do you model them? Or do you just know they exist and then you cope with it? Because I guess if you could model them, I think the topology, maybe you only deal with chains, but I know in other systems like nanoparticles that these many-body effects that most of the time arise from dispersion, van der Waals, according to the topology and the shape, they can really give completely different effects. So I'm wondering whether it could be interesting for you to model them to improve upon your qubits.
Yeah, so it's a result of a paper from a common paper, so if I don't say any mistake, from Stockholm University at University of Nottingham. This is something that I was theoretically demonstrated and modeled from basically mostly University of Nottingham. We didn't do it ourselves, but their results apply to our scheme. So, of course, depending on the trapping scheme, this will have to be improved. Yeah, but yeah. So it's a theoretical demonstration mostly.
A question in the back.
Thanks a lot for your talk. It's a question maybe for the future after your target of 2028. Do you have any ideas right now how to envision the scaling of the system?
Mm-hmm.
Because, well, trapped ion is very wonderful technology,
yep.
but ions are big. And if you want to go to, let's say, 1,000 of qubits, 10,000 or millions, which is the target for the long-term future, I think we don't know yet, or I don't know yet how do you scale with ions, and do you start to think about it because you enter the market now, you still have like 4 or 5 years before going onto the market, which also enables you to think about this for the next steps?
Yeah, so you mean the scalability after 100 ions, because we think we can trap. Okay, there have been some developments. For example, at University of Sussex, they have managed to do shuttling from one chip from another. So that's one possibility for that has been demonstrated in terms of scaling for trapped ions. There is a possibility, like I think it's of connecting different chips with entangled photons. There is a possibility of increasing the number of in 3D, increasing the number of ions inside the trap. So I think all of this consideration will have to be reconsidered in 3 to 4 years, depending on the results of the different institutes that lead the work on scalability, considering going to a higher number, higher than 100 qubits. But yeah, this is what I would answer. So yeah, try to reconsider for more than 100 qubits. What's the competitor? Where will be the competitor at that time in their development?
Thank you.
Among all the propositions I've already done.
Next one. So we're just investigating how Quantinum, for example, has proposed their 2D grid. So are you working with these single ions, so only strontium, and then doing Rydberg inhibition? Yep. And how do you compare then? I mean, I don't see how you would be outcompeting Quantinum or IonQ, just to mention those two.
Okay, so for I think Quantinum and IonQ, they work with mostly with the Møllmer-Sørensen gate. So Møllmer-Sørensen gate, they slow down after 30 to 40 qubits because they rely on the fact to give and remove some vibration phonons, which is not the case for the Rydberg gate. So Rydberg gate can go to more and more ions on their trap.
Okay, cool.
This is what I would.
Is there a publication to read on? This would be cool.
It's they have not above 10 to 20 ions, but yeah, it's a fact that the Rydberg ions interaction, dipolar interaction, doesn't rely on the motion of the ion. So
yeah, I'll follow up post.
Yeah.
Thanks.